in the back? Okay, you mean you okay, probably can hear, I hope? Yes? All right, good. All right, so I'm going to talk about a few different projects today. And all of these are collaborative with some other professor at University of Maryland. And most of these projects were really led by my students. So Shoham Day, Abhay Yadev, Sohil Shah, and Zhang Xu. And I am mostly just here to take credit for the work that they did. And these are also collaborative projects with David Jacobs, who's also at University of Maryland. So I'm going to talk about two different topics. Both of them are related to improving stochastic gradient methods for machine learning applications. And I'm going to start by talking about big batch SGD. So doing stochastic gradient descent with large batches and choosing batch sizes adaptively. And we'll talk about some of the advantages of that approach. And then we'll talk about prediction methods for solving problems related to adversarial neural networks. So that requires stochastic gradient methods for solving saddle point problems. Okay. So to begin with, I'm going to talk a bit about big batch methods and what the advantage of these methods are for solving general minimization problems in machine learning. SGD is a commonly used method for a wide range of machine learning problems, but it has some difficulties that come with it. So it's generally hard to automate stochastic gradient methods. There's problems like how do you choose step sizes, so how do you choose learning rates, how do you choose stopping conditions. And one way that we can mitigate those problems is to use larger batch sizes. And so by adaptively growing batch sizes and controlling the amount of noise in our stochastic gradient approximations, it turns out that we can solve a lot of these problems, and we can automate step size selection. We can do things like backtracking line searches and automated stopping conditions. So as a little bit of introduction, what do I mean by the stochastic gradient methods? I'll just go into some of the basics. So most machine learning problems look something like this. There is some function that measures how well our model fits points in a data set. So you might have, say, z sub I is a point in a data set, and this function f measures how well a model with parameters x fit to data point z sub I. And if you want to train the model and you want to find this optimal vector x, so the optimal model parameters, usually you minimize this loss averaged over all of the points in a data set. So you average this loss over all of the zi's. You're measuring how well it fits the entire data set, your model, and you want to find the coefficients x that minimize that error function over the entire data set. And in a more general case, you might think of your data set as being infinite. So maybe there's, say, an infinite set of images or an infinite set of objects that you want to categorize over. And in that case, we really care about is the expected value of that loss function with respect to data points chosen from the distribution of possible data points that you could have chosen. And there are many applications for this kind of formulations. Support vector machines, logistic regression, neural nets, matrix factorizations, etc. Almost any machine learning problem really fits into this framework. So to solve these sorts of minimization problems, a simple approach would be to just use gradient descent. So you could compute the gradient of this loss function. That requires computing the gradient with respect to each of these individual data terms and then averaging all of those gradients together. That gives us the gradient of the combined loss function. And then we could take a, let's see if this pointer works. Oh, maybe not. Okay. Oh, I see.
There are two big sticks on the corner. You should use the analog.
Oh, there we go. No, this works. That's fine. Thanks. Sorry about that. Okay. So then once you compute this gradient, you take a gradient descent step with learning rate alpha. So you start at a point xt, you move in the gradient direction with learning rate alpha, and you get to a new point xt plus 1. And so if we plot the contours of the function that we're minimizing, you might start with some point xt, and you take a step in the gradient direction, which hopefully points towards the minimizer of the thing that you're trying to minimize. But in practice, this sort of method is really expensive because this data set might be really large. So n might be, say, in the millions or larger. And so what we do in practice is we use stochastic gradient methods. With a stochastic gradient method, you just choose one point from your data set, and we'll approximate the gradient of the loss function by taking the gradient with respect to only one point that we've chosen from that data set. And when we did that, we got an approximation to the gradient. So in expected value, the new gradient direction is equal to the correct gradient direction, but now we have these error bars. So you only know the true gradient up to some error plus or minus sigma. And then we take a gradient descent step using the stochastic gradient direction, and then we pick a new data point, and we proceed with a different data point on the next iteration, and we keep cycling through iterations and choosing different points from our data set. When the current iterate is far away from the true minimizer, you don't really lose very much by using a stochastic gradient instead of a true gradient, because this gradient error might be really large. So if the gradient direction is huge, then having this plus or minus sigma error might not hurt you too much. Overall, you're still moving in the general direction of the minimizer. But these sorts of methods get really bad when the iterates get close to the minimizer. So when you get close to the minimizer, the noise in the gradients might actually make your approximations worse over time. So for example, if you're less than 1 unit of distance from the true minimizer, and your gradient updates, they only have accuracy plus or minus 1, you're no longer able to get closer to the minimizer using gradient updates with that level of accuracy. And if you're really close to it, in the extreme case, you might think, well, you start with your iterate at the true minimizer, and if you shouldn't move anywhere if you're using an exact gradient update, but if you have a noisy gradient update, you'll actually move away from that minimizer. So to deal with this problem, we need to find ways of making those error bars smaller over time so that the iterates continue to converge to the minimizer. And the classical way of doing that is you decrease the step size as the minimizer is approached. And so in the classical approach, you take your step size, or your learning rate alpha, and you let it approach 0 over time. And when you do that, if you look at the formula for the gradient update, it's alpha times the gradient. So when you scale down alpha, you're scaling down the error bars, you're scaling down the error in the gradient update, but you're also scaling down the component of the gradient that you're interested in. And so as a result, these methods tend to slow down over time, so you get bad asymptotic convergence rates. But there are other problems with them. In particular, it's really difficult to pick a step size schedule. There are broad theoretical frameworks for what conditions these step sizes need to satisfy to guarantee convergence. And they're usually conditions that need to be satisfied in the limit as t goes to infinity, but that doesn't really tell us anything about what an intelligent step size should be for any particular finite time. Okay, so classical deterministic gradient methods enjoy a lot of advantages that you lose once you start using these vanishing step sizes that you need to do stochastic methods. In particular, for classical deterministic gradient methods, it's easy to automatically set step sizes. So we have things like Barzilai-Borian methods or spectral methods for doing step size selection. We have things like backtracking line search methods that we can use to guarantee stability. Automated stopping conditions are easy. You can just stop when the gradient of a loss function gets small. But when you're using stochastic gradient approximations, the gradient never gets small. There's always noise in it, so it's always large. It's really difficult to assess how close you are to the minimizer. And it's also really easy to parallelize and distribute deterministic gradient methods. But it's generally difficult to distribute stochastic gradient methods and still get a good degree of scalability. So the question is, can we enjoy these advantages of deterministic gradient methods in the stochastic setting? And it turns out that we can get a lot of these advantages back if we're willing to use bigger batches. So if you go back and you look at these stochastic gradient methods, we had this situation where the iterate got relatively close to the minimizer, and we had these large error bars. And so one solution to this problem, the problem of these large error bars, was to decrease the learning rate, but you could also keep the learning rate the same, and you could just increase the batch size. So instead of computing this gradient with respect to one data point, you could compute it with respect to a larger batch of data points. Now you're averaging over more data. And then these error bars, they shrink. And now you can keep descending toward the minimizer without changing the step size. So the idea behind big batch methods is you adaptively grow the batch size over time. And this allows us to keep the learning rate the same, so we don't have to use a vanishing step size anymore. And then we get back a lot of the advantages of classical gradient methods, but we can still do it in a stochastic gradient framework. So we would like to say something about the theory of how quickly batch sizes need to grow and what sort of convergence rates we can guarantee using a fixed learning rate. So if we don't let the learning rate go to 0 and instead we increase the batch size, we'd like to have some sort of convergence theory for those sorts of methods. And it turns out that these sorts of methods have been studied in the past. although not in the context of adaptive batch sizes, but with a priori fixed sequences of batch sizes. These things have been studied. And there's a result by Richard Bird and Jorge Nos et al. From 2012 that says that we know that a gradient direction is good if the difference between our stochastic gradient direction and the true gradient direction, so the error in our gradients, is less than or equal to the magnitude of our stochastic gradient direction. So what this is essentially saying is that if the error is small relative to the magnitude of the gradient that you're trying to approximate, so if the signal-to-noise ratio of your stochastic gradient is good, then we can be guaranteed that this stochastic gradient direction is a descent direction. So this is a condition that we can put on our stochastic gradient directions that will guarantee that they always improve the solution. So one of the things that we do, so this is essentially just saying that to guarantee the descent direction, you need the error in the gradient to be relatively small, right? Relatively small error in the gradient will guarantee you a descent direction, and then the error will keep going down.
Is it like expectation or?
No, this is not in terms of expectation. So if you have an approximate gradient direction, it turns out you could take any approximate gradient direction that would satisfy this criteria, and it would still be a descent direction. I mean, there's sort of a simple geometric proof for this result. But some of our results that I'll show later will require this condition to be satisfied in expected value. Okay, but there's some questions we would like to ask. So how big is the error in the batch gradient? How big is this error? Can we measure this empirically? And also, how large does the batch size need to be to guarantee that this descent condition holds? So one of the things that we have in our analysis that's a little bit different than what's appeared previously is we make the assumption that our loss function f has a Lipschitz dependence on the data z. So we assume that the loss function changes smoothly as you vary the input data. And under that assumption, it turns out that the variance in these approximate gradients looks like the variance in the underlying data set. So we can put a bound. We can say that the expected value of this error, the expected value of the batch gradient error, is bounded by the variance in the z's, so the variance in the data set they're training on, and that's an easy thing to measure, times this Lipschitz constant, times 1 over the size of the batch. So here we have this bound. This is the expected error is bounded by this constant divided by the size of our batch. So this gives us a direct way of controlling the amount of noise in our gradients just by controlling the batch size. So the idea behind these big batch SGD methods, the way that they work in practice, you would start out by choosing some batch. So you might choose some batch, say a batch of size 3. You compute your stochastic descent direction. In addition to computing the direction, so the stochastic direction is going to be the average of the gradients over all of the data points in our batch. In addition to computing the mean of all those gradient directions, we'll also compute the variance of those gradient directions, and then that gives us the size of these error bars. And then we do an update, and then we move to a different batch. So we resample the batch, and we keep updating until we get to a point where we find that the variance in our gradients is bigger than the signal. So the norm of the variance is bigger than the norm of the mean. So in this case, we find that the noise is greater than the signal. In that case, what we can do is we increase the batch size. So we're going to increase from a batch size of 3 to a batch size of 6. When we do that, we shrink the error bars on our gradient, and then we go back and we check whether or not the signal is greater than the noise again. And if this condition fails, we can sort of keep backtracking, and we can keep increasing the batch size until it succeeds. And by doing this, we could do a stochastic gradient method where we adaptively increase the batch size to maintain the signal-to-noise ratio in the gradients. Okay, so the idea is that on each iteration, t, you begin by estimating the size of the gradient error by computing the variance in the gradient approximations. So you compute one gradient for every data point in our batch, and then we compute the variance of those approximations. Then we want to pick a batch large enough that the magnitude of the batch gradient is larger than the variance of the gradients divided by the batch size. So we're going to choose a batch size large enough to make this inequality hold. And we have this parameter theta that controls the gap between the size of the gradient and the size of the noise. So by choosing a smaller theta, you're enforcing this condition more strictly. So you pick a theta between 0 and 1. Then we'll choose some step size alpha, and we'll talk in a bit about how you would actually do that. And then we do our gradient update, just like we always do. So the only thing that we've really added is this step where we use a backtracking condition to determine what the batch size should be. And we can prove convergence of these methods under some standard assumptions. So we could have something that's essentially a strongly convex convergence result. We can also analyze this in the weakly convex case, but I'll show it in the strongly convex case because the results look a little bit simpler. So if we assume that the loss function has a Lipschitz gradient, and we also assume something called the PL inequality, which is something that's a little bit weaker than strong convexity, but in spirit it's the same as strong convexity, then we can prove a linear convergence rate of the big batch method. So we can show that in expected value, the loss function decreases linearly with this linear constant, 1 minus the strong convexity parameter over the Lipschitz constant. So that's the standard convergence rate you get for regular non-stochastic gradient descent. But in this case, there's this coefficient beta that appears here, and beta is a coefficient that depends on this parameter theta that you chose. So it depends on how strict you enforce that inequality that says that the signal needs to be greater than the noise in your gradients. So you get this linear convergence rate, and you lose a factor in your convergence rate that depends on this coefficient beta. So if you take the limit as beta goes to 1, you get back conventional gradient descent, and then you get back the same types of convergence results that you can get in the non-stochastic case. So this says that you can get a linear convergence rate using the stochastic method. Usually with stochastic methods, you get really slow convergence rates. So in the strongly convex case, you might only get, say, a 1 over k convergence rate for k iterations. In this case, we're getting a linear convergence rate for k iterations. So it seems like a bit of a free lunch. And it turns out that it's not really a free lunch because what we're really measuring here is the per iteration convergence rate. But with the big batch method, the iterations get more expensive over time. And so you can do another analysis that accounts for how many gradients you need to evaluate per iteration. And it turns out that if you count gradient evaluations, which is really a fair way to compare these kinds of methods to gradient descent methods, it turns out that to get epsilon error, so if you want to get epsilon error in the objective function, so an epsilon optimality gap, the number of gradient evaluations you need is order of 1 over epsilon, which is exactly the same as you need for conventional gradient descent. And this convergence rate is optimal in the infinite data case. So in the case where you're training on a batch of data that's potentially infinite. So in terms of convergence rates, we basically get back the exact same thing that we would with the classical stochastic gradient method. Right? So what's the advantage to using these big batch methods? Well, like I said, we can do things like backtracking, adaptive learning rates like Bars-Liborian methods, and adaptive stopping conditions. And I'm not going to talk about all these things today, but I am going to talk about, I'll just pick one to talk about. I'll talk a little bit about how you would do backtracking. So conventional gradient descent methods, you can enforce convergence using something like our Miho line search. So on each iteration, you would compute the loss function at the current iterate, you do a gradient descent step, and then you compute the loss function at the new iterate, and we hope that the loss function at the new iterate is less than the loss function at our starting point, and it has to be less by an amount that depends on the norm of the gradient, the learning rate that you chose, and also some constant c. So this is a standard backtracking formula used in the Armijo line search. With a deterministic gradient method, you would check whether this condition holds, and if it failed, then you would backtrack. So you'd throw away the current iterate, you shrink your step size, and then you try again. And so using these sort of backtracking methods, we can guarantee convergence of deterministic gradient methods. So you check this condition. If it fails, you decrease the step size, and then you just check again. And the question is this kind of simple backtracking line search approach effective for stochastic gradient methods? And for traditional stochastic gradient methods, it turns out that the answer is no. The reason why is that, so imagine as a simple example, suppose you have this function f that you want to minimize, and f is the average of two loss functions, f1 and f2, so the red function and the green function. They average out to give you this dotted function in black. And so I want to use a stochastic gradient method to minimize this black curve. And so on each iteration, I'm going to randomly sample either the red curve or the green curve. And then I could do an Armijo line search, and I could backtrack on that sampled curve to find a stable step size. But the problem is that you might be able to find a step size that's always stable, no matter where you are on either this red or this green curve. For example, the stability condition for this red curve just requires you to take a step size less than 2 over the Lipschitz constant of the gradient for this red curve. And there's a similar condition for the green curve. You could just take a learning rate that's the smaller of those two, and then you're always guaranteed to decrease your sampled loss function, either the red or the green function. So what ends up happening is you might start with an iterate, and then you randomly sample either the red or the green function, so you pick the red function, and then you take a gradient step that moves you close to the minimizer of the red function, and then you resample your loss function. So now you sample the green function, and when you take a gradient step, that moves you towards the minimizer of the green function, and the learning rate never decreases over time. You just keep sampling red and green, and the iterates just keep oscillating back and forth between those two minimizers, and there's no convergence toward the minimizer of this function in black that you're interested in the first place. But when you use big batch methods, it turns out that because our estimates of the loss function we're interested in, so our estimates of the black function are getting better over time, you can prove convergence of stochastic gradient descent in terms of decrease in the original objective. So suppose that you're using a big batch method. So we look back at this Armijo line search condition. So this time, suppose that you're using a big batch method, and you check this Armijo condition to guarantee sufficient decrease in your objective function. Then we can prove that in the strongly convex case, you get back a linear convergence rate, just like we did with a fixed step size, but this time with a line search. So we can get back a linear convergence rate, provided you start with a large enough initial step size. Right? So we can prove convergence using these sort of adaptive step size routines. Okay, so let's look at some example results. So I apologize for the complicated curves, but I wanted to kind of pack a lot of results into these graphs. So these are convergence curves. These are doing ridge regression on two different data sets. So it's a covariance matrix recovery problem and also a ridge regression on this million song database. And so we look at convergence curves for different methods. So in orange here, we see this baseline convergence curve. So this is just stochastic gradient descent, and this is using an optimized learning rate. So we assume an O of 1 over k learning rate. So we said the learning rate is going to be some constant over the iteration number. And then we did a grid search to find the optimal parameters. So we found the optimal learning rate using a grid search, and this is the convergence curve that we get. And then this convergence curve in blue, this is what you get if you do a big batch method with an optimized learning rate. So we do a little bit better using a big batch method, but also with a grid search learning rate. So this is something that would be difficult to compute in practice. And then here is in red, this curve is this is the convergence curve for the method with an Armijo backtracking line search. So in this case, we find that we actually do a little bit better in terms of gradient evaluations using a backtracking line search than we can even using an optimal learning rate. Right? So the blue curve is an optimized learning rate with a grid search. The red curve actually does a little bit better, and this is using no grid search at all. This is just doing an Armijo backtracking line search on the fly. And then finally, we can do a little bit better than that. So we have this green curve here, and this is using a Barzilai-Bourrian adaptive method to try to adaptively choose the step size. And so the Barzilai-Bourrian method can both increase and decrease the learning rate on each iteration. And then we've also done a number of experiments on neural networks. So this is training deep networks on SciPar 10 and also the Street View house number data set. So this is a digit classification data set. It's sort of like MNIST, but harder. And so these are accuracy versus time curves, so higher is better. So as the algorithm trains, what happens to the accuracy on the test data set? And you'll see this light blue curve. This is a big batch step size with an Armijo backtracking line search. And then this dark blue curve, this is a fine-tuned stochastic gradient descent using a tuned learning rate schedule. So we did a grid search to find the best learning rate parameters, and we get an accuracy curve that looks like this blue curve, and then we actually do a little bit better using a Barzilai-Borwein method with no grid search at all over the parameters. For the SciFAR data set, we find that the big batch method with our Meo line search does a tiny bit difference. It's really hard to see on these curves. It actually comes in a tiny bit worse than a fine-tuned stochastic gradient descent. You lose a fraction of a percentage in accuracy. But all in all, we find that you can get similar performance to what you could achieve using a fine-tuned neural net, but you can do it automatically using these sort of adaptive line search rules. And one thing I'll mention is we've also done comparisons. So this using, say, ADA delta, which is a variant of ADAgrad. We've done experiments using Atom and a whole bunch of other types of neural net optimizers that you can easily combine with these sorts of big batch methods. Okay, so I'm going to move on, and I'm going to talk about saddle point problems for neural networks. And actually, before I talk about neural networks, I'm going to talk about saddle point problems for general convex problems, and then how we can take some of the tricks that we use on convex problems and we can port them over to difficult non-convex neural network problems. So in image processing, very often we like to solve saddle point problems that have a general formulation that looks something like this. So I have two functions. I have f and I have g, and I want to minimize f with respect to the set of variables x. I want to maximize g, or negative g, with respect to this set of variables y. And then these two sets of variables, x and y, they talk to each other through this cross-link term, the inner product of ax and y. So there's this bilinear term through which these terms interact. Usually it is assumed that these functions f and g are simple in the sense that we can evaluate their proximal operators efficiently. So there are many applications of these types of saddle point formulations. We review some of them in our recent review paper, and I'm not going to go too much into detail here, but things like linear programming, image segmentation, scaled lasso problems, TVL1 denoising, democratic representation problems, and signal processing. Many of you are probably familiar with these things, so I'm not going to go into too many details on the applications. But one thing I will mention is that there are a variety of different well-known methods for finding these saddle points. One that we're particularly interested in is these primal dual methods that were first popularized by Shamble and Pak in 2010. And the way these methods work, so we have this saddle point problem. I want to take this composite loss function. I want to minimize for x, and I want to maximize for y. And so we can do this by alternating between gradient descent steps for x and gradient ascent steps for y. So to begin with, we do a gradient descent step on x that only looks at the crosslink term. So we start at a point xk, we march down the gradient of the crosslink term, and then we do a backward gradient descent to deal with this term f. So we do a proximal step on this loss function f. So we can think of those two steps together as a minimization for x. And then there's this prediction step. The prediction step, it turns out that this is what we're interested in the neural network case. The prediction step says that you define this iterate x bar, and you do that by taking the current iterate, xk plus 1, that's the result from the previous gradient descent step, and then I look at the difference between xk and xk plus 1, so this is the direction you just marched in, and I'm going to add that direction back to xk plus 1. So I'm saying, however far you moved on the last iteration, move that far again. So move extra far. That's called a prediction step, so it's sort of predicting the direction that your iterates are moving in. And then I have a gradient ascent step. So I take a gradient ascent step for y. I do a forward step on the crosslink term and a backward step on the objective term g. But when I compute these gradients, I compute the gradients at the point x bar. So I'm not using the iterate xk plus 1, I'm using the predicted iterate x bar to compute where these gradients are. So these methods are known to be very stable. They're really effective for a wide range of problems in image processing. But one of the difficulties with these methods is that the convergence tends to be very sensitive to the step size parameters. So you have tau, which is your step size parameter for the x update, that's your primal update. I have sigma, which is my step size parameter for the y update, which I'll call the dual update. And convergence is generally very sensitive to these parameters. And we can measure that sensitivity by using residuals for the problem. So I'll define the primal residual. The primal residual is the derivative of this loss function with respect to x. The dual residual is the derivative with respect to y. And if you found a saddle point that's minimal for x and maximal for y, then both of those derivatives should be 0. And so I can measure the convergence of this algorithm by looking at those residuals. And what we find is that there's trade-offs between those residuals. And you can control those trade-offs by using these step size parameters. So if I were to choose a large value for tau, so tau is the step size for the primal update, and you can compensate for that by choosing a small sigma, so you choose a small step size for the dual update. If you do that, then you drive this primal residual down really quickly, but the dual residual sort of lingers and converges slowly. And then on the other end of the trade-off, I could choose a small value for tau, in which case I get a slower decrease in the primal residual, but then I can choose a really large value for sigma, so I can really aggressively decrease the dual error, and then I get a really small dual residual. And for the method to converge, you need both of these two things to be small, and so what you might think to do is you might balance these two residuals. So you might modulate your step size over time and track these residuals, and you try to adjust your step sizes so that these two residuals are roughly the same size. So in our 2014 NIPS paper, we have convergence analysis for these kinds of methods. And we show, there's some mumbo jumbo that I'll sort of talk you through here, but we have this parameter theta that controls the amount of adaptivity in the algorithm. So it measures the relative change between your step sizes. And we can show that provided that adaptivity level is summable, so it has to decrease over time, you can prove convergence. And to get convergence, you need to enforce one of two stability conditions. First, the product of your step sizes needs to be less than the spectral radius, the reciprocal of the spectral radius of A transpose A, where A is the matrix that appeared in the cross-link term. But in practice, you might not actually know what that spectral radius is, and so we also have a backtracking line search condition. So you evaluate this inequality. It just requires you to look at the norms of the differences between iterates and simple inner products that you actually have to compute during the algorithm anyways. So you evaluate this backtracking line search condition, and if it fails, then your step sizes are too big, and you cut them both in half, and you check this condition again. And so this allows you to do these sorts of primal dual methods without having to know anything about the spectral properties of the problem that you're trying to solve. And recently we've also been able to prove that you get a worst case 1/k rate in an ergodic sense. So if we actually apply these sorts of methods to convex problems, we find that we can get really good convergence properties without having so much user oversight. So these are convergence curves showing error over time, so lower is better. And we have two convergence curves here. These show the primal and dual, sorry, not the primal and dual, these show the objective function gap decay over time for a method with a tuned primal and dual step size. So we've picked a constant tau and a constant sigma, but we tune them using a grid search to get the best possible decrease in the objective function. And we actually find that you can do much better using adaptive methods. So here's the curves for two different adaptive methods. One is using knowledge of the spectral radius of A, and one is just using a backtracking line search. We find that they both perform about the same, but using these adaptive methods, you don't have to make any choices about what your tau or your sigma should be, and you don't need to know anything about the spectral properties of your problem. And we find that one of the reasons why these methods can do so much better than a constant step size is that they evolve the step size over time. So here we see a plot where this is plotting the value of tau and sigma, so blue is tau and green is sigma, over time. And as the algorithm proceeds, we find that it tends to favor a really large aggressive value of tau at the beginning, and then there's sort of a trade-off over time where tau starts to decrease and sigma starts to increase. And so you can actually do better using one of these adaptive step size schedules that can change your parameters over time than using a constant step size schedule that might be potentially less efficient. So this is all stuff for convex problems, and I said I was going to tell you about neural networks. So what can I say about neural nets? So interestingly, it turns out that recently there's been an explosion of interest in saddle point problems involving neural networks. And the reason why is because of the appearance of what are called adversarial models. And one in particular that I'll talk about is called generative adversarial networks. And there's many different applications for generative adversarial models, but I'm just going to talk about sort of a simple case here. So generative adversarial networks, or GANs, they model a data distribution. So you might have data drawn from some distribution. In the simple case, you might be drawing from a Gaussian distribution, and I give you a set of data points on that distribution, so points drawn from that Gaussian. In a more complicated and abstract sense, you might think of images as coming from some distribution, and you don't really know what that distribution is, but you can sample images. So you could look at something like the CIFAR 10 data set, and there's just a 10 by 10 tiling of images from that data set. Or you might have some process for farming images from the internet, and you might think there's some infinite distribution of natural images, and you can acquire a finite sample of them. And from that finite sample, I want to use a neural network to model what this underlying distribution looks like. And then once you have that underlying distribution, you can use it to continue sampling. So you can use your model of the distribution to produce artificial images that I'll call fake images. So these are images that are produced from your model of what the distribution looks like. So the simple application of GANs is you can use it to sample this model distribution and produce new images from that distribution. But you can also use these for more complicated things. So for example, suppose that you want to generate a caption from an image. If you're given an image, you want to automatically generate a text caption for it. You can use adversarial models to generate images from captions. So you can provide a description for the image and then produce an image from that description. And you can do a lot of other really complicated human-like tasks using these sorts of adversarial models. So how do these GANs work? Well, imagine that I wanted to train a neural network to produce fake images. So I want to produce things that look like real images. One way I might construct such a network is I would take a network that as an input to the network, it just takes a vector of random noise. So I take a random Gaussian vector, I feed it into my network, and then I have a deconvolutional network that increases the dimensionality using a very deep network architecture, and it spits out an image. So we'll call this the fake image. And if you wanted to train this network, what you might need is some sort of loss function that measures image quality. So you have a loss function that measures how imagey the output of the network is, so how much it looks like a natural image. And you would want to do some sort of training process on this that minimizes this loss. And this loss, it's defined as an expectation over z, so expectation over the random input of the imaginess of the output of your network. So the problem with this kind of loss function is that we don't really have good characterizations, at least not in a variational framework, good characterizations for what makes an image good. For example, the classical characterization would be something like natural images have small total variation. And that's a really good image prior for various types of image recovery tasks. But for something as sophisticated as this, that isn't really good. If you just tell this network to output something with small total variation, you'll just get blobby things that don't really look like images. So what we need is an image prior that has more of a human-like performance in discerning between what looks like an image and what doesn't. And so we can do that using a discriminator network. So what we could do is we could train a neural network to discriminate between real-looking images and fake-looking images. And then we could, so we have this neural network that I'll call D, and then we could train the generator network to try to fool the discriminator network. We could train the generator network to produce things that the discriminator thinks are real. So we would be minimizing a loss function that looks like this. It's the expectation over z, so the random inputs, of a loss function that loss function acts on the discriminator network, which takes as an input the generator. So you take some value z, the generator produces an image, the discriminator tells you whether it's real or not, and the training process consists of adjusting the weights in this generator network to minimize this loss so that the discriminator thinks that the output of the generator is real. And it turns out if you train a neural network like this, and then you freeze this discriminator, and then you try to train the generator, this generator is just going to exploit various nuances of the discriminator, and you don't get anything that works very well. So what we do in practice is we train the discriminator simultaneously with the generator. So as we are training the generator, we're also going to update the weights of the discriminator so that we can increase the performance of the discriminator as we're increasing the performance of the generator, and these things are going to compete against one another. So we have this initial loss term. So the generator, the weights of the generator are being tuned to minimize this loss, which corresponds to fooling the discriminator into thinking that fake images are real. At the same time, we're going to update the weights of the discriminator to increase this loss. So the discriminator weights are trying to increase that loss function. So the discriminator wants to be able to tell effectively when it's being given a fake image. And then we're also occasionally going to feed a real image, so a real natural image into the discriminator, and the discriminator has to be able to say when the image that's been given is real. So this creates a saddle point formulation, so these networks are competing against one another. The generator is trying to decrease this loss function to fool the discriminator, and the discriminator is trying to increase the loss function, right, to not be fooled. And when we do this, we can produce neural networks that really effectively produce these sorts of natural images, and I'll show some of these later. So there's very simple stochastic gradient methods that people use to train these sorts of adversarial networks, and usually they just use alternating gradient descent. So given some abstract loss function that depends on generator and discriminator weights, I want to minimize this thing for G, the generator weights. I want to maximize it for D, the discriminator weights. I could start out by computing a stochastic gradient of this loss function with respect to the generator weights, and then I do a gradient update to minimize that loss. And then I do a stochastic gradient computation to get the derivative with respect to the discriminator weights, and I would do a gradient update. Oops, this is supposed to be a D update, not a G update. Sorry about that. So now we do an ascent step to update the discriminator weights. But one thing that these methods are missing that we know works really well in the convex literature is we're missing this prediction step. Right? In the convex literature, after we do our initial primal descent step, we do this look-ahead step. And then when we compute the gradients with respect to our discriminator weights, what we should be using is this predicted value of the gradient weights, this look-ahead. So in the convex setting, we know that these kind of prediction methods can really stabilize our saddle point solvers. And in some situations, you can actually prove better convergence rates and larger step sizes when these sorts of prediction methods are used. And the question is, can you port this idea over and use this for stochastic methods for training neural networks? And there's a few different questions that we would like to ask. First question is, do prediction methods still converge in the stochastic context? So most of these methods have been studied in the non-stochastic case. Do these prediction methods still work in the stochastic setting? Can we prove this in theory? And what can we say for non-convex problems like GANs? And then another question you might ask is, do these prediction methods work with more sophisticated types of neural network solvers like Adam? And it turns out we can answer these questions either using theory or using experiments. So to start with, one of the things that we were looking for in our recent work was sort of an intuitive explanation for why these sorts of predictor methods, so why the predictor step in these sorts of Shambo-Pock algorithms is effective. And now there's a lot of work that does algebraic derivations that use that prediction step to get better convergence rates, but maybe there's some intuitive reason that we can put behind it. So here's something that's sort of intuitive and sort of mathematical at the same time. Suppose that we want to solve a simple bilinear saddle point problem. So I have some full rank matrix K, and I want to find a saddle point of V transpose KU, where I'm minimizing for U and I'm maximizing for V. Right? So every smooth saddle point problem that has a Taylor approximation looks like this if you zoom in close enough around the saddle. Okay? So we can write down a method without prediction. So without prediction, you would start some iterate U, and you would march down the derivative of this loss with step size t, and you'd start at an iterate v, and you'd march up the loss with some step size sigma. And we can rewrite these updates as a finite difference method. So if I look at this first update equation, I've got a uk plus 1 and a uk, and there's a step size t. What I'll do is I'll put both of the u's on the same side, and I'll divide by t. And so now I have a uk plus 1 minus uk divided by my step size t. I can do the same thing for v, so I get something that looks like this finite difference equation. Right? And these update rules, they look like a finite difference discretization of a dynamical system. So uk plus 1 minus uk over the step size, that's an approximation of the time derivative for u. Right? So I can write this as a dynamical system. The change in u over change in t, that's like the derivative with respect to u. So the derivative with respect of u with respect to t, I'll write that as u dot is equal to kv. And I have v dot, the derivative of v with respect to t, is a constant times ku. And one thing I would like to point out, in the original version of the slide, I used the Leibniz notation for this derivative, but I switched it to the Newton notation because I didn't want to be locked out of my hotel room when I got back to Robinson College. Okay, So anyways, this is a simple dynamical system. Some of you will probably recognize this. It's just a simple harmonic oscillator in 2 dimensions. It's this canonical form of a harmonic oscillator. And so this, if you look at this in UV space, this just rotates around an ellipse, an elliptical orbit, and it just orbits this indefinitely, and it never collapses toward the origin. So this method never converges. Now, is it reasonable to think that you'll get this kind of asymptotic behavior? Like I said, these sorts of dynamical system approximations, they assume that the step size is small, so that this quantity looks like the time derivative. In the stochastic setting, you always have a step size that's vanishing as k increases, right? At least the way that you do these conventional stochastic gradient methods. So as the method proceeds, you eventually get to a regime where the step size is very small, and then this just looks like a harmonic oscillator, and it never converges toward the origin, okay? So we could also look at this in the case that you have a prediction step. So let's write these equations again with a prediction step. So this time the V update involves this quantity, UK, plus the difference between, difference in UK plus 1 and UK. So this is the prediction step. This should actually be a UK plus 1. Sorry about the notation snafu. So we can rewrite this V update as a dynamical system. So we put these 2 V's together on this side here, and we divide by T. And what we find is that we have something that looks like the same dynamical system we had before, except now you have this UK plus 1 minus UK term. And when you divide that by T, you get an update term that involves the time derivative on this right-hand side here. And that shows up in our dynamical system. So now the derivative of V with respect to time is equal to k times u plus a constant times k times u dot, time derivative with respect to u. And so that is the time discretization of a dynamical system for a harmonic oscillator with damping. And the harmonic oscillator with damping spirals in toward the origin and converges. So I think this gives a sort of intuitive explanation for why these things might work. If you look at these from a dynamical system perspective, it turns out that that prediction term gives you damping in this oscillation and allows the method to converge on these sorts of bilinear saddles. So that's sort of a not so rigorous way of looking at what happens in the limit as the step size goes to 0. It also doesn't really account for stochasticity, and so we can actually prove a more rigorous theoretical result. So suppose that you want to solve a saddle point problem. We'll assume that the loss is convex concave, so we have to make some nice assumptions about the geometry of the problem if we want to be able to prove a convergence rate. We'll assume that the loss function is Lipschitz smooth. The gradient of the loss function is Lipschitz smooth with respect to V. We assume that the gradients remain bounded, which is a standard assumption in convergence theory for stochastic methods in the weakly convex case. And we'll assume that you're solving the problem on a bounded domain. And in that case, we can prove that this predictor primal dual method converges in terms of the primal dual optimality gap with rate 1 over square root of k in an ergodic sense. So that gives us some theoretical reasons to believe that this sort of thing should converge. But then the question is, what can you say about neural nets? Well, in neural networks, things are pathologically non-convex. So theory is nice, but it doesn't really tell us much about what happens in the neural network case. So for neural nets, people oftentimes say the proof is in the pudding. And it turns out that at Cambridge, people actually eat pudding. So we're going to actually get to see some experiments. So in the GAN case, for neural networks, one thing that people are interested in is avoiding what are called collapse problems. So it's really easy to cook up stable stochastic gradient methods when you're trying to solve a simple convex minimization problem, because even if a problem is non-convex, when you get close enough to a minimizer, the function looks like a bowl, and you get trapped at the bottom of this bowl. It's really difficult, assuming your step size isn't so big that you jump out of here, you can pretty much rely on your method converging, and there's theoretical results that indicate that should be the case even for non-convex problems. But for saddle point problems, you can't really be so sure that the method will be stable. For example, so here's an example of a saddle point function. We want to converge to the saddle, and we alternate between gradient descent steps, which are shown in black, and gradient ascent steps, which are shown in white. If your gradient descent step is much more powerful than your ascent step, then you're eventually just going to slide off the side of the saddle point function, and the objective will just go to negative infinity. So in the neural network world, people refer to that sort of event as a collapse. A collapse is when you slide off the side of this loss surface, and you're unable to converge to a saddle point. And this is a big problem for training adversarial nets. So this is an example. These are synthetic images that we generated using DC GAN, which is a really well-known generative adversarial network by Radford and company. So here's some results. These are images produced by DC GAN, and these are images produced by DC GAN when we introduce this prediction step into the training. If you run them both for long enough, you'll eventually get good results from either of them. But what we find is that the training method for DC GAN without prediction tends to be really unstable, and you get these really well-defined collapse events. So here's the loss function for the generator, and here's the loss function for the discriminator, and we find that you get these events where you slide off the side of the loss function, the generator loss spikes to nearly infinity, which means that the generator is performing poorly, and you'll see that the discriminator loss basically goes down to 0. So this is a situation where the discriminator is dominating the generator, and so you're sliding off the side of the loss surface. And when these events happen, we can show some images that are sampled from the generator, and you basically get junk images. You get things that look like noise, or things that look like simple geometric objects with a noisy background. But if you run this for long enough and you stop at the right time, you don't stop too close to a collapse, you can get nice looking results. But with prediction, we find that you get these really nice, smooth, predictable loss curves, and you never really have these collapse events. And I think one of the really exciting things about these prediction methods is you can actually train much faster than you could without prediction. So this is an example of DC GAN training with 10 times the learning rate. So now we're going to try to push the limit and see if we can train 10 times as fast. And we find that DC GAN without prediction is completely unstable. So in this case, we basically just get back random static from the predictor, but we still get really nice looking images from DC GAN if we use this prediction method to stabilize the training. And we see that in the loss curves as well. So if you try to train with these really aggressive learning rates without prediction, the loss function for the discriminator shoots up to nearly infinity almost immediately. The loss function for the generator almost doesn't train at all. If you really zoom in close, you see there's very small oscillations here. But there's almost no training in the generator whatsoever, whereas with a prediction method, these are still really stable, and you can train these sorts of methods really quickly using these types of predictions. So in our recent paper, we have a bunch of experiments, not just on generative adversarial models, but we do domain adaptation problems, fair classifier problems. So for example, you can train neural network classifiers that are blind to issues like gender or race or other input factors using adversarial methods. So these are images generated using a GAN trained on the LSUN data set, which is a data set of images of bedrooms. So these are synthetic bedroom images, right? So these are images supposed to look like images of bedrooms, but none of these are actual real images. These are all just produced by a neural network using random inputs. Okay, so to wrap up, I talked about two different topics. I talked about big batch SGD. So big batch SGD uses a method of adaptively growing batch sizes over time. And by doing that, we can avoid this issue of vanishing step sizes. So we don't have to let our step sizes go to 0 anymore. And that also allows us to use things like Barge-Liborian methods and our Miho line search methods to automate stochastic gradient methods. I also talked about prediction methods for saddle point problems. So we looked at these types of predictor-corrector methods that are frequently learned for convex saddle point problems. And it turns out that we can port those over to stochastic training problems. And we can prove convergence results if we're willing to make convexity assumptions. And for neural nets, we find empirically that we can train much faster with prediction methods than we can without prediction methods, and that these types of prediction methods avoid the collapse problems that really plague these sort of adversarial networks in many practical situations. So thank you very much. So here's some of the papers I talked about, and these are the names of the students that I worked with on those papers. Thanks.
Thank you. We have time for one question. Yes.
How does your big batch stochastic gradient descent compare with stochastic aggregated or average gradient descent?
There's this whole literature on variance reduction methods, and SAG sort of fits into the variance reduction framework. So our results, for variance reduction, you can prove faster convergence rates than you can prove without variance reduction. The results that we prove for big batch methods are comparable to what you get for non-variance reduction gradient descent. But I said that that's optimal, and that's because we study the infinite data case. So variance reduction methods exploit the fact that you have a finite data batch in order to get better convergence rates on that data batch. But the question is whether or not you can, so one of the reasons we don't study the finite data case is that when you have a growing batch size, asymptotically, when you get close enough to the minimizer, the best strategy turns out to be to take the full batch and use all the data. And in that case, you asymptotically get the same performance as you would using a classical gradient method. And you can port over the same types of convergence results. So we study the problem in the infinite data setting. And in the infinite data setting, it's really difficult to compare variance reduction and non-variance reduction methods.
Just classical SGD.
What's that?
So does your result improve over doing classical SGD and averaging the iterates? Like 1 over epsilon?
What do you mean over averaging the iterates?
Usually you...
The ergodic convergence. That's a good question. We haven't really done comparisons directly with the ergodic iterates. At least in the machine learning context, I think it's sort of unusual to use the ergodic average as an iterate. But we don't have. Well, I actually don't have an answer to that because I don't know off the top of my head what the ergodic
without averaging
iterates look like.
Without averaging in the strongly convex case.
In the strongly convex case, we find that we can usually do a little bit better using big batch over a finely tuned gradient method. But I think that the real advantages are just in the automation. So like I said, from a theoretical standpoint, you can't prove that we get a better convergence rate. I think the real advantages are just that you can use things like backtracking line searches and such. In the experiments that we've done, we did a little bit better using big batch methods than we could using a finely tuned SGD. But you know, we haven't looked at every possible data set and every possible problem, and so I don't think those empirical results mean that big batch is better than SGD with generality. But I do think that what you can say with generality is that big batch offers a lot of automation advantages that you can't get with vanishing step size methods.
Okay, we postpone additional questions to the break,
Sure.
which takes place now, and we reconvene again at 10 past 11. So thanks again to both speakers.